Dear students, in today's session, I am going to explain one of the derivation of chapter number 7, that is alternating current, and the topic is series RLC circuit. So it's an AC circuit, so there is RLC. R stands for resistance, L stands for inductance, and C stands for capacitance. So therefore there are three circuit elements which are connected. First one is the resistor, and then a coil which is an inductor, and then a device called capacitor. So RLC. So resistor, inductor, capacitor. Resistor offers resistance, inductor offers inductance, which is self-inductance, and capacitor offers capacitance. Now this is connected to an AC source, which is an alternating current source. So this is the alternating current source. Now since all these three elements are in series, the current through the resistance, inductance and capacitance is same. Let it be I. And due to this current, there will be voltage across the resistor, which is a V suffix R, which is given by I into R, which is the Ohm's law. Across the inductor, the voltage is a VL, which is I into XL. XL is called inductive reactance. It is opposition offered by the inductor. Okay. Then we have VC, which is I into XC. This is called a capacitive reactance. Same current, different voltage because of different opposition. R is the resistance, XL is inductive reactance, and XC is a capacitive reactance. Okay. Now between voltage and the current, the phase relation is not same in all the three cases. In resistor, voltage and current are in phase. So I can draw the phasor diagram here, where current and the voltage and the current, they are in phase. That means the phase difference between them is 0. So which clearly indicates that the phase difference between V and I are 0 because both are along the same direction. In inductor, voltage leads current by 90 degree. VL leads I by 90 degree. Whereas in capacitor, current leads voltage by 90 degree. And now we have to find the voltage across the combination and the voltage across the resistor, the inductor and capacitor. If V is the voltage across the combination, then what is the relation between V, VR, VL and VC? That is what we are going to derive using this particular diagram, which is called phasor diagram. So we have to simplify three vectors. They are in three different directions. So that's why V is not equal to VR plus VL plus VC, not equal, because of the phase relation. So first let us simplify VL and VC. Angle between them is 180 degree, and I am going to assume that VL is greater than VC. VC can be greater than VL. VC can be equal to VL. All three possibilities are there. So we are going to assume that VL is greater than VC. If VL is greater than VC, the resultant of VL and VC will be VL minus VC, because the angle between them is 180 degree. Apply vector addition. When theta is 180 degree, the resultant is P minus Q. And that resultant will be along VL. Why? Because we have assumed VL is greater than VC. So therefore this will be VL minus VC. Now I have to find the resultant of VL minus VC and VR. So construct a parallelogram. In this case, we get a rectangle, and the diagonal gives the resultant, which is V. So therefore now what is the angle between this and this phasor, which is 90 degree. So when theta is 90 degree, R is equal to root of P square plus Q square format. So that's why V is equal to root of VR square plus VL minus VC the whole square. that is root of. Now substitute, what is VR from here? VR is nothing but IR. So square it, you will get I square R square plus, what is VL from here? I into XL minus I into XC the whole square. See here I is common, and when you take I out of this bracket you will get I square. Now for both the terms I square is common. When you take I square out of it, but there is a root, for the I square apply the root, what do you get? You will get I. So what is left? R square plus XL minus XC the whole square, so which is V. Now if you refer R, XL and XC here, these are all constant, and that effective constant is denoted by Z, where Z is equal to root of R square plus XL minus XC the whole square. So what do we call that effective opposition? It's called impedance. It's called impedance. Now in this diagram, the effective voltage is here, which we also call as a RMS voltage, and current is here, and they make an angle phi, and that phi is called phase difference. This we can calculate. You can use a cos phi, you can use a tan phi, you can use a sin phi. So commonly used format is tan phi. So tan phi is equal to, it is opposite by adjacent. Opposite is VL minus VC here, VL minus VC, by adjacent is VR. So again, if you apply these voltages and if you substitute, I is common for both numerator and denominator, that will cancel, giving XL minus XC by R. So this is one such derivation, and numerical based on this is very important. So refer the notes and then prepare for the exam. And if you have any such derivation where you want me to explain, I will explain once again the important derivations of the different chapters. Thank you.